Okay. Well, thanks for the invitation to give a talk here, and also for the wonderful program that we have had here. Thanks for hosting us. So I'm told that this is going to be an informal talk geared towards non-experts, and that's what I'm going to assume, even though I see many experts here. So please ignore some of the elementary things that I will have to say. So a lot of it is going to be a review kind of thing, where we got to here, where we are, and a little bit about what's happening now. So both aspects I will try to say some things about. The review I will do would be based on what Witten did a long time ago, so I will review some of the basic starting points of the relations between topology and quantum field theories. And then I will connect to more modern things within string theory and how that comes about. The part that I myself have been involved with is related to joint works with, a number of people from old times, with Witten and also with Gopal Kumar, Oguri, and more recently with Gukov and Pei and Putrov. So this is through a decades kind of span of different kinds of works that I'm going to talk about. So it's going to be, I'm not going to be very good with referencing, and that's not the point of this talk. It's going to be a general overview of what's going on in this field, and that's what my aim is. So given the various backgrounds, so let me start very basic, where things kind of became topological within quantum field theory setup. And this was around 80, where Witten was studying aspects of supersymmetric systems, supersymmetric theories. And what he noticed was that there are interesting things that are kind of invariant within the quantum field theory language. And what that meant in this context was that he had a theory, he was studying a theory, in fact a quantum mechanics theory, for the simplest case, where the Hilbert space involved both bosonic as well as fermionic states, namely states which had -1 to the f plus 1 and -1 to the f minus 1. And he looked at the spectrum of the energies, and you can show that whenever you have a boson, you also will have a fermionic state, and they can be transformed from one to the other using the supersymmetry charge operator by the symmetries of the supersymmetry, except for the ground state. So for the ground states, where the energy is zero, the supersymmetry does not map the bosons to the fermions, they just map it to the zero. So then the number of bosons and fermions does not have to be equal at the ground state, but they're equal all the way up. And so therefore, if you study a trace of -1 to the f, e to the minus beta h, you get the number of bosons minus the number of fermions only at the zero energy contributes, because all the other ones cancel out. And this is an integer that you can compute, which is independent of beta. So this was kind of surprising, that something in a computation does not depend on the beta, which almost every other kind of computation you do does depend on. And moreover, if you change the parameters of the theory, since things pair up together, the net number doesn't change. So it's not only independent of beta, it is independent of compact perturbations of your theory. If you just take little perturbation, it doesn't change. So these numbers are invariants of quantum field theory. Or in this case, the simplest case would be the quantum mechanics case, invariance of supersymmetric theory. So a very simple example of what these kind of numbers mean, what do they signify, was nicely exemplified by the following example. You take one-dimensional sigma models, which means you take maps from the circle to a manifold. So you have an action which looks like integral over time of dtx with some metric on the manifold. So you think about x as coordinate of the manifold, and you write this action, the most obvious action you can write down, plus some fermionic terms to make the theory supersymmetric. And in this kind of context, it turns out these numbers count things like cohomology states of the manifold. So some invariants, some aspects of topology of the manifold came to be playing the role of ground states of supersymmetric theories, and you can view these in physics language in terms of some quantum field theory path integral. So this was kind of the beginning of this relation between supersymmetry and topology. You can nicely capture some aspects of topology with simple computations in supersymmetric systems. However, one has to be, even this one, this example already has a lesson for us. You see, we have put a -1 to the f here. If we had not put a -1 to the f in the trace, then it would not have been an invariant, because then you're just counting the bosons and fermions with a plus sign, so there's no cancellation. And therefore, this would not be beta independent, or it will not be independent of perturbations either. So it's crucial to have this -1 to the f. What that means in the language is that on the circle, we are taking the fermions to be periodic boundary conditions. So we have periodic boundary conditions, and in particular, a crucial fact this implies is that we have a constant spinner. For periodic boundary condition, we do have a constant spinner. And that's what allows us to have supersymmetry on that circle. If we put anti-periodic boundary condition for fermions, it means we don't have this term, and then we don't have a constant spinner anymore, because we have anti-periodic boundary condition for fermions. So it's crucial to have a constant spinner for this whole thing to work. Okay, so that's one lesson we have here. Now, you might say, okay, this is interesting. Why don't we generalize it? We know there are supersymmetric theories in other dimensions. For example, in 4 dimensions. So do the same thing. Take a time to be the circle, and take your space to be a 3-dimensional space. Some complicated manifold, whatever you want. And do the same thing. You can study the theory on this one, and you get ground states of this one. So that means that for this theory in 4 dimension, you can associate to the 3 manifold some states. Number of bosons minus the fermions. And for whatever supersymmetric theory you have, will be a machine where you give an x and it gives you an answer for the number of bosons minus the fermion, computing something which just depends on the 3 manifold, a topological invariant. Because these numbers don't change under perturbation, so if you change the metric or this and that, it shouldn't change. So that's the idea. It doesn't quite work. Why doesn't it work? Well, the reason it doesn't work is that on a general 3 manifold, you don't have constant spinners. You don't have covariantly constant spinners. Therefore, it's the analog of the problem of what would have happened if you did not have a -1 to the f. So for a general theory, for a general supersymmetric theory and a 3 manifold, you're out of luck. It doesn't work. So the idea that supersymmetric theories are powerful gets a stumbling block. What do you do in such a situation? So this was a puzzle. So people said, okay, in that case, you can just, instead of doing general 3 manifold, in physics we're not interested in general 3 manifold sometimes, we just do 3-dimensional torus, periodic box. For those cases, you are fine. So you can always do something like a periodic box, but for a mathematical interest of it, namely, if you want to associate to 3 manifolds some physical invariant, like computations of the type here, then you need to make sense out of supersymmetry in these situations. So that was the puzzle. Now, more generally, you could have had a 4-dimensional manifold. In fact, if you're not dividing space and time, if you do a Euclidean version, for example, you can talk about the 4 manifold, and you try to do some computation for the 4 manifold, similar to getting some interesting numbers for the partition function. What do you do and how you can do it? This was a problem that Witten managed to solve in late 80s using what is called the twisting of supersymmetry. Twisting, which I will explain what it means. And the idea was the following. So the rotation group or Lorentz group in the Euclidean language is SO4 for 4 manifold, which you can think about as SU2 left times SU2 right, as usual. And if you have a spinner, it decomposes to a doublet of one and a singlet of the other, plus a singlet of one and a doublet of the other. So the spinner decomposes to spinner of doublet of 2 and 1 and 1 and 2. None of these are covariantly constant in priori because there's no, in general manifold, for manifold, we don't have a covariantly constant spinner. However, if you have n equal to 2 supersymmetry in 4 dimensions, there's an extra quantum number which is the rotation of an SU2 which rotates these 2 supercharges together. So you have an extra symmetry, an extra global symmetry, which is called the SU2R symmetry. And if you include that, there will be an extra doublet. Each one of these spinners will have an extra doublet quantum number for this SU2. So what Witten noticed is that if you define a new quantum number for the left part, so change the SU2 left by taking a diagonal sum of what you used to have plus the other guy plus the SU2R coming from this guy. what that happens is that then you get a tensor product of these 2 and 2 instead. So the spinner, which used to be a spinner and the singlet and so on, now becomes, from 2 tensor 2, you get 3 plus 1, as usual. So therefore, you end up getting a singlet out of this guy plus 3, 1. And similarly for the other one, you get the 2, 2. So if you just tensor them, you get this representation. And finally, you have gotten a scalar. This one, a covariantly constant scalar, exists on any manifold. So therefore, this allowed him to be able to define supersymmetric theories on arbitrary form manifolds. Now, this required n equal to 2 supersymmetry, and so using n equal to 2 supersymmetry and arbitrary form manifold, he managed to define a topological theory for arbitrary form manifold. And this actually, his motivation actually was to try to realize what is called Donaldson theory. So Donaldson had already defined certain invariants for form manifolds, studying instantons of gauge theories on form manifolds. And Witten managed to write a quantum field theory, in this case, n equal to supersymmetric Yang-Mills theory with SU2 gauge group, which realized the theory that Donaldson had written down mathematically. So he realized the mathematical theory in the language of a quantum field theory. Later on, when Seiberg and Witten managed to get the infrared degrees of freedom of the SU2 n equal to 2 theory, that gives a new way of actually computing the Donaldson invariants, which turned out to be very powerful and very surprising for mathematicians, and has led to many interesting results and rigorous math statements that was quite unexpected for the math community. So this was kind of the impact that this had. So this is kind of like a supersymmetric theories and relation to topological theories, kind of in the 80s and later a little bit in the 90s, early 90s. But parallel to this and along this side, there was another development. Again, this was originated mainly by some people, but in particular by work of Witten on Chern-Simons theory. So this is another kind of topological theory. In this case, the theory did not depend on details. So here, for example, the answer did not depend on the radius of the circle beta. This topological theory, the theory does not depend on radius of the manifold or the metric on the manifold just because the action doesn't depend on it. Yes?
So what does the twisting mean?
Twisting means doing something which we usually do not do in physics. That is, some fermions become scalars or spin 1 and so on. So it's not the usual quantum numbers we associate. So in other words, the spinners which used to be spinner doublet now becomes like vectorial or tensorial. So it's something which violates the spin statistics theorem, for example. So this was kind of done in a way to get some invariance for the physics. Later on, when I talk about string theory, we will see that actually string theory in a unitary way realizes the same mechanism. So this idea is even though this sounds like it was just made to get an invariant out of this, is actually very natural, it turns out. So in the context of topological theories of the other type, the theory itself does not depend on any metric. And Chern-Simons theory is the prime example of this. And what that means is that you take an action, which is the Chern-Simons term, a term like this. So you take A, which is a gauge field in some group like SUN. You take a term like this, and you have an action something like this, with some integer coefficient in front of it. This theory, if I write down like this, it does not depend on any metric data. I didn't tell you what the metric is. A is a 1 form, and these are all 3 forms you can integrate. I did not need the metric to define it. So it's morally topological, and therefore if I start with a particular 3 manifold and compute a partition function, it will depend on the level and the choice of the group, and it'll be some number, and that's an invariant of the 3 manifold. And this is known as in particular, as Witten-Reshetikhin-Turayev invariance. You can compute using partition function of Chern-Simons. In fact, you can do more because you can introduce some source terms to try to play the role of Wilson lines. So if you take a particular loop or knot, and let me call it gamma, and compute the path order exponential of the gauge field along this knot, if you compute its correlation function, it will also depend only on the knot type. Because the metric doesn't play any role. So where you put the knot doesn't matter, but of course you cannot cross the knot. If you cross it, you get a different answer. For any given kind of a knot, you get a particular answer. So this gives you knot invariance. Okay, so this was all done. This was all beautifully done, and it was connected to various different things. First of all, it was related to two-dimensional conformal field theory. This is all in the late 80s. But also later on, it got applied to condensed matter system in the context of fractional quantum Hall effect. And in particular, the Wilson lines here was what one can imagine as having being anion degree of freedoms. And in this context, these computations of the Wilson loop amplitudes and so on get a particularly interesting meaning about what happens if you take, for example, anyons around each other or twist them around this way or that way. The amplitude for such processes is computed using these knot invariants. So it's a very nice application in this condensed matter system. So again, topological. And as you can see, we have two different classes of topological theories. One in 3 dimension and has no metric in it. And the other one kind of uses supersymmetry. A priori, these look completely disconnected. Now, one thing which was already noticed a while back was that if you compute these knot invariants, for example, the expectation value of the Wilson line, you find that the answer, when expanded in terms of the parameter q, where q can be viewed as related to the coupling constant of Chern-Simon, e to the 2 pi I over k. So if you define that to be q, it was found that this has an integer expansion. You get a kind of polynomial kind of things with coefficients which are integers, as if you're counting something. But counting what? This was not a counting of anything. This was a partition function. But it looked like you're counting something. And it was mysterious. Why are you counting something? Because there was no counting being done. Just a partition function. So it's mysterious why this happened. Okay. I think this is the basic status of the study. Oh, there's one more example I want to say. Going on to string theory, which is the following. So there was one relation between these two sides, the supersymmetric side and the Chern-Simon side. Namely, so I told you about examples in one-dimensional quantum field theories with supersymmetry and also the four-dimensional one. But there's also a two-dimensional supersymmetric theory, which corresponds to sigma models. So you take a Riemann surface, and you map it to some space, some manifold. So under suitable conditions, well, this can have supersymmetry. So these are what's called supersymmetric sigma models for your manifold there, depending on the manifold. And if the manifold is suitable, then you can again do the same trick you did that you saw I explained, which is called this twisting that within it. You can do it also for these cases. So you can get topological sigma models, which does not depend on the shape of the manifold or this and that, similar to what it did not depend on the four-manifold case. Okay, what's the relation potential between this side and that side? Well, it was observed again by Witten that if you take this space to be a Calabi threefold, the six-dimensional manifolds that are a favorite of many string theorists, so it's a six-dimensional manifold, and you take in it a Lagrangian three-dimensional subspace. So for example, you can put a manifold M here and view the six-dimensional manifold as like a phase space of that space, cotangent of M. If you put some object here, this is now a three-dimensional space. And if you imagine having holes on this Riemann surface and allow the holes to end on this Lagrangian subspace, so you get some kind of a space like this. So you have a Riemann surface map to this like that one. You compute the topological theory in this context. You find some degrees of freedom living on this three-dimensional space. And if you view this as part of a string theory where you integrate over the shape and sizes of this Riemann surface, you find that the theory living on this three-dimensional subspace is Chern-Simon's theory. So Chern-Simons theory arises from the target space viewpoint of a would-be string theory, a would-be topological string theory. So there was kind of an indirect relation between one theory which is topological, which is supersymmetric, and this other one which has no relation with metric at all. They kind of got related.
And the gauge group, how it shows up here?
Sorry?
The gauge group of Chern-Simons.
The gauge group showed up here in the following way. So for the general one, you cannot do it. But what you get is that on this Lagrangian one, you put a number of branes, which is how many stacks of them you put. If you put n of them, you get un Chern-Simons theory. So the number of them is this. And that's because each one of these holes will end up on one of these guys. And so for each loop, each hole, you get a factor of n. And this is exactly the same as the 't Hooft diagram rules, where the boundaries of the diagram gets a factor of n. So you can realize UN gauge theories this way. You can also extend it to SO case, but not to the E case, and so exceptional groups are not going to be realizable this way. Okay.
It seems there are two kinds of topologies here, one of the left-hand side and one of the right-hand side. In the 4D case, there was no right-hand, the map from S1 times X3 was not to some other manifold.
That's correct. This was not a sigma model. It was a gauge theory. So in other words, in 2 dimensions, to write an interesting 2-dimensional theory, there are many ways you can do it. One way is to think about it as a sigma model. In higher dimensions, sigma models are not interesting. Gauge theories are more interesting. Like 4-dimensional gauge theory is what was the origin of the n=2 system that, for example, Witten studied in connection with Donaldson theory. But it's a theory living in 4 dimensions. This is a theory living in 2 dimensions, even though it's coming from a sigma model whose variables describe a higher dimensional space. Okay, I think this is the main thing I wanted to say. Now, I think the main points are there. Now I want to switch to string theory. So this is kind of the background, and I want to kind of explain how these ingredients become unified in string theory. So there's the development of string theory led us to rethink about all this in a different way, which is my main point here. So let's see. So first of all, it's kind of a philosophical point, but you might ask, why are we interested in these low-dimensional questions like 4-manifold invariance or 3-manifold invariance or not invariance? Well, one answer would be because we are physicists and we like 3 dimensions and 4 dimensions space-time and all that. It's a reasonable answer. But surprisingly, that's not the reason mathematicians are interested in this. So mathematicians are interested because these are precisely the most interesting manifolds to study for the invariance of. Surprisingly. So in other words, quite regardless of whether we lived in this universe or not, this would have been more interesting to study for them independently. That's quite shocking, that these are 3 and 4 manifolds are quite interesting, and 4 in particular is among the hardest one to understand, the structure of 4 manifolds. So that's one point, that the 3 and 4 is interesting. So low dimension, surprisingly, is interesting for mathematicians regardless. Even if you had all possible dimensions to study, 4 would be something you really want to understand. That's surprising. And then in that context, you would say, okay, great, string theory. What is the dimension of string theory? Well, it's not 10 to the power of 500. It's also low. Well, it's not 3 or 4, but 10, 11, 12 is kind of low compared to what it could be. It could have been 10 to the 10,000. So it is low, but you might say, well, why did it miss it? Why did string theory miss the right dimensions? 3 and 4 are the more interesting one. Why did it go all the way up to 10 or 11 or 12 or whatnot? Why are we going even that much up? So in perspective of it is actually still low. And actually I want to explain why actually it exactly is the right dimensions to have objects which is going to be relevant precisely for 3 and 4 dimensional theories. So that's what I'm trying to explain. So string theory is a theory of quantum gravity, so it has gravity in it in the game. But the examples mainly I talked about, for example, the to gauge theory and Donaldson theory, had no gravity in them. It was a theory of gauge degrees of freedom without gravity involved. Those theories were the ones which ended up giving interesting topological theories. So string theory, you might think, is useless. We are having, gravity in the game, so how are we going to be using that to get things like topological invariance? Well, the good thing about it is that in string theory we have interesting objects. On these objects live interesting degrees of freedom which can be decoupled from gravity. You can take the limit of m Planck going to infinity, decouple gravity, and study these systems in isolation. That will give you interesting new systems, and that's actually what we found to be the case. So string theory led to new systems that we had not expected them to exist before the advances in string theory. And in particular, we learned that all the way up to 6 dimensions, there can be non-trivial interacting quantum systems. Non-trivial interacting quantum systems. This, at some point, people had thought maybe 4 might be the highest dimension where you can have interesting quantum systems, non-trivial. But we have now learned that in the context of string theory, we can actually end up with non-trivial quantum system interacting in a very non-trivial way, all the way up to 6 dimensions. The ones that we really do understand, again, in these dimensions are the supersymmetric ones, which is excellent for topological theories, as you saw. So supersymmetric ones in 6th dimension. And in fact, more than that, we have found superconformal theories in these dimensions. In fact, the classification of superconformal theories shows that the highest dimension you can ever get is 6 dimensions. There's no superconformal theory beyond 6 dimensions. And nicely, string theory gives you systems which are nice, non-trivial, and 6-dimensional, and interacting, and that's the highest dimension. Everything else you get should descend from that, because there's nothing else, nothing higher. 3 and 4 are surprisingly close to 6. Now, I will try to make it a bit even more tantalizing. Why is it interestingly close to 6, and why 6 is the right dimension for this?
Are these string theories or field theories?
Good question. So these are kind of like field theories in the sense that string theory has graviton in it and so on. So these is a sector in the string theory, but you can decouple it. So in other words, you can study that field theory kind of thing decoupled from gravity. Now, having said that, I have to clarify. It's not field theory of the type we know very easily about. It's not like point particle field theory. No. More precisely, what we learned that the 6D theories are made of objects which are tensionless strings, not like massless particles. So it's at the conformal point they're tensionless strings, even though there's no gravity in the discussion. So there's different kinds of string comes in and gives you tensionless behavior, and that drives the criticality. That's why you get the conformal point. So these are interesting theories in their own right. Okay. Now, what do we know? What are these? Well, there are actually 2 classes. 2 classes of these 6D theories, depending on the amount of supersymmetry. The one which has the bigger supersymmetry, which is called 2, 0 supersymmetry, and the one which has the less supersymmetry, which is 1, 0 supersymmetry. So there are 2 classes. This class is completely classified. We know exactly we don't have a proof, but we believe we have classified it. We think we know the full list of 2, 0 superconformal theories in 6 dimensions. And these are classified by simply laced groups, ADE. Even though we are using a group label to label them, this actually has no gauge symmetry in 6 dimensions. So it's not a gauge symmetry with this group. But somehow ADE comes to label these theories. So how does ADE show up? Well, it turns out that there are different ways of realizing these theories in string theory. One version of them is by singularities of a space. You take your space and you look at the singular point on the space. You have a curvature is infinite, and it's hard to study what that point is. So then what you do is you resolve the singularity, you change the metric, and you change it a little bit to see how it looks like. And once you do that, this space you have to resolve the singularity, and instead you end up getting spheres which touch each other, like the Dynkin diagram for the A group, or the Dynkin diagram for the D group, or the Dynkin diagrams for the E group, etc. So the ADE labels how the spheres resolve themselves into the ADE diagrams. So this is a mnemonic, if you wish, of how to label these theories. They also end up relating to gauge symmetries if you go one dimension down. It turns out that if you compactify these theories on a circle, go down to 5 dimensions, in 5 dimensions you do get ADE gauge symmetries. So there is a relation with gauge symmetry, but in 6 dimensions where it starts life, it is not gauge theory, but non-trivial interacting theory, and we have a huge amount of evidence for the existence of these theories, and we can compute many aspects of these theories, even though we cannot compute everything about them, but we can compute some things. The simplest version of them, the A case, which is this one, can be also described much simpler in terms of a stack of parallel 5 branes. So you take n 5 branes and 5 branes, and 5 branes are objects in M theory which are 6-dimensional, and you just put stack of them and next to each other. So we can think about them as defects, 5 plus 1-dimensional defects in M theory. And if you take n of these defects next to each other, they realize this 2, 0 theory. So there's a way of thinking about these defects in that language. Okay. Now, what can we do with these theories? Well, this theory is, let's start with this. I haven't told you about the 1, 0 theory, so let me put this on the back burner for now. Let's talk about 2, 0 theory for now. So it's a 6-dimensional theory, so what do we want to do? We want to compactify it and study it on lower dimensional theory. You can put it on T2, for example, times the 4 manifold. So this is a 6-dimensional space, T2 times the 4 manifold. And if you do that, if you go down on a T2, what you end up getting is actually an n equals to 4 gauge theory with gauge group ADE. Where the torus, usually we draw the torus like this with some parameters. If you think about this as size 1, and if you think about this point on a complex plane tau, tau turns out to be related to the coupling constant of the gauge theory, something like this. Maybe there's a factor of 8 pi or 4 pi something here. Anyhow, so you get some factor like this where these are the coupling and the theta angle of a gauge theory. So this is a parameter of this theory. You compactify it on this theory and you compute the partition function of this n equals to 4, and it turns out this is exactly the kind of systems that Witten, an extension of what Witten did, works. Namely, if you take from n equal to 2 supersymmetry, extend it to n equals to 4, you can compute the partition function a priori. And the answer depends on the coupling constant of the gauge theory. And here, this ends up to be exactly equal to the partition function of M5 brane because it realizes n equals to 4 supersymmetric systems. Moreover, this explains the strong-weak duality because the symmetries of the torus has SL2Z symmetry, which means that if you replace tau with minus 1 over tau, which corresponds to exchanging these two sides, is a natural symmetry. So the symmetries of the geometry, in this case 6 dimension, encode strong-weak dualities of the 4-dimensional gauge theories. So it's quite a non-trivial connection. And this is, but as you can see, we ended up with a theory which has more supersymmetry than the one that was interesting for Donaldson theory, n equal to 2. And you get similar kind of system in the topological system that the Donaldson theory gives you, but a bit higher. How about the Chern-Simons theory? Well, the Chern-Simons theory can be obtained in a different way. Namely, you take, again, the 6-dimensional space, but don't break it up into T2 times x4, but just write it as x3 times a cigar times a circle. And in such a way that as you go around the circle, you rotate this by q equals to e to the I theta. So in other words, as you go around the circle, you don't come back to the same point on the cigar. You actually rotate the cigar by an angle given by this q. So if you take n M5 branes in this geometry with this angle, it turns out that this gives you the partition function of Chern-Simons theory with this parameter q as q being e to the 2 pi I over k of the Chern-Simons theory with the gauge group which is SUN on the manifold X3. So the six-dimensional theory computes in this way partition functions of Chern-Simons. Now, we were getting integer things, as I told you, when we were doing the knots. So how does the knots and integer things come in? Yes?
Then it means that theta cannot be arbitrary. It has to be.
So this generalizes it, because you can think about this Chern-Simons theory as being extended to one higher dimension.
Okay.
So theta is not quantized anymore, but gives you the same partition function. So you end up getting some partition function in this form, and you can introduce knots in a similar way. Namely, so if you have, for example, a three manifold here, you can have one three manifold here, another three manifold here, which intersect over a knot. And once this happens, you end up getting the expectation value of the Wilson loops along that knot, and you can compute it. But there's more you can do, because you now have a Hilbert space. So you can compute the partition function, but you can also remember that there's actually a Hilbert space. So you find that the fact that these numbers were coming out, the partition function was an key to the n, these an's are actually counting the dimension of the Hilbert space of a given spin. So the counting of the objects that gives you the integer expansion of the knot invariance for Chern-Simon is nothing but counting the Hilbert space of this six-dimensional theory. So it demystifies the integrality of the Chern-Simon, and it has to do with this extra circle that was missing in the description of Chern-Simon. This was also missing, but in particular this circle gives the role of a Hilbert space structure, the time, which allows you to count, and this gives you an integer expansion. Now, this has actually been interesting because it actually extends the Chern-Simons theory in the following way. This cigar is actually a part of R4. In other words, more generally, there's a cotangent of this cigar is in the geometry. So the particles here have two things. One is they have a spin along the cigar, and that spin is captured by powers of Q. But there is also this normal direction, the cotangent direction. There's a rotation perpendicular to this cigar. There's an extra U1. So you can refine the Hilbert space and have a doubly charged object. One is the spin, the other one is the charge in the normal direction. So there's an extra gradation, extra charge, so to speak, which is missing in the Chern-Simon partition function. This has been what is called a refinement of Chern-Simon's theory. That is, you can actually get new information from this Hilbert space description of Chern-Simon theory that is more refined than Chern-Simon. In other words, if you compute the knot invariance using Chern-Simon theory, sometimes two knots might give you the same partition function, but they have a different Hilbert space because you are not taking into account the charge in the other direction. So this was first, from the math perspective, was discovered by Khovanov, and the physics interpretation ended up being what I just told you, involving objects in the M theory, which involves M2 branes ending on these guys, which you can count. So these led to completely different formulation of Chern-Simon's theory, which is one of the subjects that is being discussed in this workshop. So I talked about this 2-0 case, and now let me also tell you a little bit about the 1-0 case. The 1-0 case has half the supersymmetry, and half the supersymmetry, when you come down to 4 dimension, ends up being exactly what you want for n equal to 2. So it's exactly the Donaldson version of the Donaldson theory that Witten was studying. So there's exactly the same amount of supersymmetry as the minimal you could have had in 4 dimension. So let me tell you a little more about these 1,0 theories and their properties. So these 1,0 theories are also related to singularities of string theory, and you have to resolve them and to see how it looks like. And they look somewhat like the Dynkin diagrams I told you about. But the singularity structure does not just give you ADE, it gives you a new classes of diagrams, which is similar to ADE. But in the case of the ADE, the self-intersection of any vector v dot v was equal to 2. Here, the self-intersections are not just 2. The length squared associated with them can be any number from 1 to 12. So you can kind of have it's a different kind of a Dynkin diagram. It's not the usual ADE. And moreover, you associate certain groups. There are some rules of what groups you can associate in addition to each node. So we have kind of understood the classification of these theories, and it has to do with the singularities of elliptic Calabi threefold. So there's some nice study there. But the main point is that it's kind of a diagrammatic way of thinking about these classifications. You take these theories, and you ask, can I put it on arbitrary four manifold? Can you actually do this? And this is the magic of why I'm saying string theory is smart to know four manifolds are good. The 1,0 theories, which is the generic highest dimensional supersymmetric theories, has a symmetry which is SU2R symmetry. In other words, the symmetry that you need to twist the theory is SU2. So you could not do a topological theory of these guys in 6 dimension or 5 dimensions, but you can do it in 4 dimension and lower. So you need a 6-dimensional object for it to end up having this property to do 4 manifold invariants in this case. So it beautifully fits together that the highest dimension supersymmetric systems has exactly the amount of supersymmetry for you to be able to do this study of 4 manifold invariants. So also from physics side, it is magical. So string theory and so on comes up even though you start with 10, 11 and so on. It zooms down to an invariance involving 4 manifolds and topological aspect of these 4 manifolds. And the nice thing is that once you study them and putting on 4 manifolds, you end up getting 2-dimensional partition functions, and these are modular forms because of this symmetries of the torus that I just was mentioning to you. And this actually has turned out to be interesting for completely different reasons for mathematicians who study what's called topological modular forms. And so these aspects of this theory and how that fits with the other one is actually currently being studied. So that's part of some of the discussions we're having. So I think I was supposed to more or less end at this time, so I will stop at this time. And if you have any question, I'll be glad to answer. Thanks.
So what happens about 6 dimensions? You can wriggle out of everything.
So there is no there's a classification of the superconformal symmetries by Nam shows that 6 is the highest dimension you can have. So that's a fact of life. So you cannot decouple gravity really in these higher dimensions. You have some extra degrees of freedom that you cannot have a nice conformal system. In lower dimensions you can have.
You mentioned you didn't mention supergravity at all.
Yes. I should have.
Which has higher than n equals 2 symmetries available in 4 dimensions, right?
So if you take the maximum supersymmetry in the highest dimension,
yeah,
it will have n equals to 8 in 4 dimension if you come. Yes, that's correct.
How do they?
Okay, so let's go one by one. So if you're interested in a quantum system without gravity, you cannot have n equals to 8. Because if n equals to 8, if you have any multiple, it completes it to graviton. So you cannot get that. So if you would want to get...
Your n equals 2 is without gravity.
Exactly. So that's the surprise. That even though the word string theory comes to discussion, we are interested in non-gravitational aspects of string theory, which might sound strange because the point of string theory was to try to describe quantum gravity. But it turns out, that's the main point here, is that string theory has taught us about quantum systems which are decoupled from gravity and has given an insight which was not part of what we were looking for. So that includes these objects which have no gravity in them. It's decoupled gravity from them.
Yeah, so if we go one step further, compact by 4 of the 6 dimension, do we get the 2-dimensional safety? Or?
Yes, that's exactly what happens. So in other words, we actually think of it differently. We compactify the theory on 4 manifold, and you get a theory in 2 dimensions, which turns out to have 0,1 supersymmetry.
Okay.
And then you can put it on a torus or do whatever else you want with it. So precisely classifying these theories, this gets related to exactly understanding what kind of 0,1 symmetries supersymmetric theories you get.
But then, so then we get some known duality in the 2-dimensional safety, something like that? Or?
Sometimes we do. For some of these theories, for example, the 2,0 theories, So people did put this on a four manifold, and they say, oh, this kind of change of the four manifold, viewing it this way or that way, which is obviously the same in four manifold, gives you a duality in two dimensions. So people have already done exactly that kind of duality. It's what's called actually it turns out to be triality, for example. It's more than duality. So three objects get related. So yes, so people have used this picture to come up with new statements of dualities.
In your cigar construction, do you actually get some reconstruction of the boundary or co-boundary for the Cumrun homology?
So yes. So in this so the statement from the physics language is that what is the relation of the Hovanov homology and the physics language here? So in the physics language we have a supersymmetry, and the supersymmetry gives us that way to distinguish ground states. The BPS states of that ground state is exactly the cohomology that Hovanov, the analog of the cohomology that Hovanov introduced in this context. Yes.
So what defines the cohomology itself in the physics context?
Supersymmetry.
So what kind of boundary operator is there?
Well, it depends on in what language should I say it, because
in whatever language works for you.
So the statement is that. So I would say it the language that we understand best. So typically what we have, so you have a three manifold and you have a knot in it. So what we are interested in is, so in these knots you typically have some M2 branes which end on these knots. We are interested in counting these M2 branes. Holomorphic objects which end on these guys. That's the physics language. Counting these guys. Now, more specifically, this counting gets related in the Hilbert space to finding the ground states of a supersymmetric system in a given sector, which is similar to how I started the talk, namely by going to the ground state and counting the elements of the Hilbert space.
Okay. As far as six-dimensional systems without gravity coming from string theory is concerned, we also have the little string theories.
Yes.
Have these played any role?
People have speculated, but they haven't played a role yet. But I won't be surprised if they do, because they are in some sense decoupled. I didn't bring it up. I didn't mean to say they are not interesting, but I think they're just a minor extension of these superconformal theories. Which we wrote a paper about, yes, with this gentleman.
Because you emphasize this point that going for conformal field theories, why you limit yourself by conformal, because your original, say, quantum mechanical stuff
yes.
is not conformal, right?
Yes. So this is related, I would say, to this question. Yeah. Namely, the little string ones is not conformal in the sense that there's a scale in it.
Yeah.
So yes, so one could also study them. Certainly, conformal ones are the more interesting, more simpler classes, but you could enlarge it to include them too.
So for the cigar, is it possible to, consider a limit where the cigar takes infinitesimal size, so that we're talking actually about a 4D, whatever gauge theory?
That's actually how people do duality. So that's exactly that picture you just said, like taking the limit where the cigar looks like a semi-infinite line, and mixing up with this one is the kind of picture people talk about in the language of saying, Chern-Simon action, of course, could be a boundary of a four-dimensional F wedge F term in 4D. That's related to the fact that in that context, the theta angle is not quantized, for example. Okay, if it arises as a boundary term. In this context, it arises as a boundary term.
And what exactly is the focus then of the current program?
The current program has, as you can see, I hope I didn't give the impression that we have figured out everything.
Yeah.
No, we have a lot of things to do here. So first of all, related to the question that was asked, how do you actually compute these things? I mean, it's one thing to say, well, it's a ground state, and the other is actually go out and compute. How do you compute it? What's the method? And those are not easy. So the Hovanov's theory and so on, people have tried hard to do how to define and do the computations. In some cases they can. In physics we have some cases where we know how to compute it. So those are parts of the efforts. Others are these new ideas about how you get, for example, this class into the game, and for example these topological modular form having to do with compactification of four manifolds, so new four manifold invariants, or relation of them between the original four-dimensional invariants that Seiberg and Witten had defined, and what does it have to do with the Hilbert space in the three-dimensional theory. So all these different things in different contexts, so it's a connection of all this. The point I was hopefully trying to emphasize in this talk is the unity of it. It looks completely scattered otherwise. It looks like this, that, this, but they are actually, in the context of string theory or M theory, they come together as just studying the allowed quantum systems which are consistent in 6 dimension and their compactifications. That's the unifying principle. It simplifies discussion, and supersymmetry is underlying the whole thing, including the Transients theory. So that's the kind of a link between all of them.
Like an open-ended question. Are there interesting mathematical invariants people know in 3 and 4 dimensions that till now we have no idea how to realize in physics? Probably many or not.
Well, there's always debate of what that means in physics. I think that the belief of physicists is that no, there's no such thing. But
it's not known, for example, I believe, whether Donaldson invariants are enough to distinguish all 4 manifolds.
No, he has a different question.
I know he has a different question,
Yeah.
but I'm just giving an elementary example of the difference in the way that physicists and mathematicians will look at the invariants.
Yeah, so the answer to the question of whether or not there are cases that mathematicians say, there's this invariant, give me the quantum field that computes it. At least I don't know a priori there's an example of that or not. I think that the belief is that we can construct one. Now, whether or not, as Dave is saying, that's enough to distinguish 4 manifolds, that's a different question. That's a much harder question, and we don't know that for sure. Even for 3 manifolds, well, there are conjectures about them in 3 manifolds and so on. Some people think, for example, the Humphrey polynomials, which is these Transients partition functions that you can do for knots, might be enough to distinguish all knots. May or may not, we don't know. So those are different questions.
Please.
Can I ask a question about going up in dimension? So some of what we know about 6-dimensional conformal field theories comes from the holographic correspondence, ADS7. So in particular, we can work out the conformal anomalies of those theories by a gravity calculation. And there's no obstruction to going up in dimension. And as a mathematical physicist, as somebody interested in conformal geometry, you can go up in dimension. You can calculate conformal invariants of ADS8, ADS9, and so on. You would say that presumably that these seem to be very much in the swampland from the perspective of string theory.
Yes.
But what would these things that one can rigorously mathematically calculate? Can you think of an interpretation in terms of physics, or do you think it's just inextricably, entwined? They only have a meaning in the closed string sector. They're not going to have a meaning in the open string sector.
Sorry, you mean these ADS8 or ADS9?
Yeah, if you go up into ADS8, ADS9.
I would think that they wouldn't exist. They wouldn't be a complete theory. You might be able to get some semi-classical thing out of them, but they would not complete themselves to a full quantum system. If they did, they would be in contradiction with the facts we know about string theory. What the dimension of superconformal, the highest dimension of supersymmetry is 6, and so on. So there shouldn't be a supersymmetric system, and
sure. But we can still calculate rigorously mathematically various conformal invariants.
Semi-classical.
Well, just from
not a complete. You don't have a complete quantum system. If you had a complete quantum system, that would be a different statement. That would just say that it doesn't have any completion. I would say that the picture would be that you can only do classically, semi-classical.
Okay, thank you.
Thank you.